our last type. And this is, we're going to talk about alternating series. We've already kind of talked about alternating series and what they are. Do you remember what an alternating series should look like?
-1 raised to some power.
-1 to the n, and then we would have the a sub n, or it could look like -1 to the n plus 1 a sub n. Alright, so alternating, when I say it's an alternating series, what's alternating? The signs. It's going positive, negative, or negative, positive, negative, positive. When we deal with an alternating series, the first thing we're normally going to look at is actually the absolute value of the series. So like if I have the absolute value of -1 to the n a sub n, what would that equal? Just a sub n. Because notice most of the tests that we've learned before, it always says that we have positive terms, right? So what we're normally going to do if I have an alternating series is first look at the absolute value of it. The reason why is because we have what is called the absolute convergence theorem. Which says, if the absolute value of a series converges, so if we want to think of this graphically, so if I have a series and I have some terms that are positive, some terms that are negative, if I make all of those terms positive, if I make all of those terms positive and it adds up to a finite number, then what happens if I make some of them negative and subtract stuff? It'll still be a finite number. And what we say here is if the absolute value of it converges, we say that it converges absolutely. This is kind of like when we say a limit equals infinity. Alright, if a limit equals infinity, what do we know about that limit? Does it exist or does it not exist? It does not exist, but we're being more precise. We're saying that if a limit equals to infinity, we're saying it doesn't exist because it goes up to some impossibly large number. Correct? When I say that a series converges absolutely, I'm just saying this series converges, but not only does it converge, I know that if I take away that negative, it is also going to converge. Alright, an example of that is, let's look if I have -1 to the n over n squared. The whole point I'm trying to get here is if I have an alternating series, the first thing I'm going to look at is the absolute value of it. So, what's the absolute value of that? 1 over n squared. What is this going to do? Why? Therefore, this is going to converge. So if the absolute value of this converges, what is this going to do?
Converge.
This is going to converge absolutely. What is going to say converge absolutely? By the absolute convergence theorem. but we're not going to worry about that. What do you mean, why does the n go away? Because I took the absolute value. I'm taking the absolute value. What is absolute? When I take the absolute value of something, what am I doing? Making everything positive. What makes something an alternating series? It goes from positive, negative, positive, negative, positive, negative. So by taking the absolute value, I'm saying instead of having some positive terms and some negative terms, I now have all positive terms. Yes?
Is there a way to find the actual sum or no?
No.
You can't do it like with a telescope or with...
But these won't.
What's that?
No, because they don't cancel out. See,
Also, it doesn't matter, it's the negative sum is on the top of the column, we just don't do it.
it'll always be on top.
What if it doesn't?
That's what we're going to talk about in a second. Alright? Let me ask you just kind of, this series right here, the summation of 1 over n squared, if it was just that, does that converge absolutely?
No. No.
Yeah. Because what is the absolute value of 1 over n squared? 1 over n squared. What I'm trying to say is, all the terms we've dealt with so far have all been positive terms. So technically, if they converge, their absolute value converges, because it's the same thing, right? So really what I'm trying to say is, like, converges absolutely is only means something when we have terms that aren't all positive. Okay? Now, let's look at, so